Okay, so good afternoon, everyone. Welcome to this Friday afternoon colloquium. Yeah, I'm sorry for our speaker that there are not so many people in the audience, but all the important and relevant people are here. So we will, they will act as multipliers. Yeah, it's really a big pleasure to introduce Professor Carsten Maple from the University of Warwick. Yeah, one because Warwick University and Stellenbosch University are good friends. Yeah. And two, because he's really an authority in cybersecurity and related things. Yeah. And he happens to be in Cape Town for a big African ID conference, and we managed to convince him to catch an Uber and come to Stellenbosch. Yeah, no, so thank you very much for that effort. Yeah. So he's the director of the Academic Center of Excellence in Cybersecurity Research, and of course, a professor of cyber systems engineering at the University of Warwick. He's also the director of the research innovation at Edge AI, and many, many, many others. Things that I won't read because you all of you can read yourselves, and it's on his on his bio. Yeah. But what is maybe interesting to mention, and I'm sure he will speak about it just now, is that he's also leading the research on a framework for responsible AI in finance, and those are things that we're also very much interested in, and maybe we can find a way to collaborate on something while you're here with us. Yeah.
Super.
So, Carsten, thank you very much for the trouble of joining us this afternoon, and we are very curious to listen to your talk. Thank you.
Thanks so much, Francesco, and thanks everyone. It's a pleasure to be here today. So, as we've mentioned, I'm here for a big conference with a lot of governments around the world that are meeting in Africa for ID for Africa. So ID for Africa is an annual conference. It's the 10th one this year. I've actually traveled to South Africa before. I really do like it here. But last year I managed to travel to many different countries I hadn't been to before, talking about how we make digital identity and the infrastructure that underpins it, make it trustworthy. So I was in Benin recently, Kigali and other places. So thanks very much, Francesco, for inviting me. So I want to say, because I got asked just beforehand about, I'm a professor, as you said, at the University of Warwick. So this is some work we're doing at Warwick, but also some work we're doing at the Alan Turing Institute. So the Alan Turing Institute is the National Institute for Data Science and AI in the UK. So it was established in 2015 by the UK government. It was called for it in a letter from the chief scientific advisor to the then Prime Minister, David Cameron, saying we needed a national institute. And the winning consortium was Warwick with Oxford, Cambridge, UCL in London, and Edinburgh. Now it encompasses many other universities. So this work is a collaboration from both of those, and it's a pleasure to be here. So I should say that this work is down to a whole bunch of people, too many to mention, actually. But my main collaborator is a professor at Cambridge. He's also a special advisor at the Turing, was a researcher at large, John Crowcroft. He will be in town on Sunday for the same event. Yeah, and he's Marconi Professor at Cambridge and a Turing Fellow, and Mark Hooper, who is Technical Development Manager at the Turing Institute. And if I was to list everyone, there must be about 15 people at least I would have to list. So I haven't listed those specifically, because I'm not talking about all of their work, actually. One thing that's important is that this work, I should acknowledge, is funded by the Bill and Melinda Gates Foundation. So they funded this work a little while ago. So we're just started our 5th year of the program. In fact, ID for Africa, when I first went, was in Johannesburg, actually, but I didn't see much of it apart from the airport and the conference center. So that would have been back in 2019. And We've just finished, after 4 years, the Gates Foundation, like the work that we've done at the Turing, and have just extended it for another 3 years. And it's a $9 million project. Should say that one thing is we're doing fundamental research, and I'll present some of that today. I'll start actually with giving quite a broad brush about some of the challenges. And the reason for that, Francesco, is so you can see some of the breadth of work. At Warwick, I tend to have around 16 PhD students. One just got through his Viva this week, so it's about 16, 20 research fellows, and around 20 at the Turing as well. So I do quite a bit of fundamental work, but what we try and see is how that can pull through. And one way that we do that is something called MOSIP. It's the Modular Open Source Identity Platform. It's funded by a bunch of organizations, including the Bill and Melinda Gates Foundation. And what that does is it provides a platform for countries to develop their identity system. So it's open source, it's free. It's being used in Philippines and a number of other countries, around 13 at the moment. But what it does is it gives us an opportunity to see the fundamental research that we do. How can it have a route to having some relevance? So digital identity is really empowering. I was fortunate enough to present some of our work to the Indian government. India has the largest digital identity program in the world. 1.4 billion people have what's called an Aadhaar card. And the power of that card has really been seen recently, because from the start, after this project started, the global pandemic hit, and that necessitated giving aid to many people and giving health provision. The problem is, when you don't have an identity system, you have to be careful about who do you give resource to. If you've got something that's you can rely on as an identity system, it means you can rapidly give funds out, and you know that people are only claiming once, and you know who it's going to. So it helps reduce fraud. So when I went to India recently, I really saw the power of that. You know, see, there's many different ways people could just, you know, very much mobile payment systems, and actually in Africa has been pretty good for M-Pesa for many years, really showing innovation. So digital ideas, there's power to reach many people, and it's brilliant because many people have access to a smartphone. Actually, I should rephrase that: a feature phone, perhaps not a smartphone, but something that's got some work. And we know that digital identity can unlock economic value, as McKinsey found out. But the problem is, we have this digital identity, and I don't know if anyone knows the story of digital identity in the UK. Been somewhat challenging in the UK. There is a lot of pushback against the digital identity system. There was one going to come in just before 2012 when Cameron abolished the Digital Identity Act. And the reason is people feel that they might be surveilled. And there was a good, a really interesting lesson that could be seen around what happened with contact tracing with the pandemic. I don't believe pandemic was a long time ago, but I mentioned it so many times just recently in some talks. But there were concerns about centralized access to who was contacting whom, etc. And in the UK and Europe, there was a very big discussion. So it moved to a decentralized model. And that was really interesting because GCHQ, who were supporting some of the work, had wanted a more centralized model, but there was a big pushback. And with the Bill and Melinda Gates Foundation, what they said is, hang on, if we're going to have this that empowers people, we don't want it to be used badly for surveillance. And I'll show you some of the things that have gone wrong, unfortunately. So there was a whole load of questions around this that we're exploring. So as I said, in discussion with Bill and Melinda Gates Foundation, we said, okay, we need trustworthy digital identity. And that's because there are incentives to misuse or commit fraud within systems. And because, as I said, with Aadhaar, 1.4 billion and other countries embedding these nationwide identity systems, the value of compromising that identity becomes significant. So when we created this program, I remember my one of my press people saying, yeah, we're going to push some press out saying this is, you know, we want to create trusted identity systems. And I called her up on that. I said, it's not trusted identity system, it's trustworthy. So it's an important distinction, and it's a real distinction that we could bear in mind for AI, for example. Right now, there's a lot of work on trustworthy AI. What's important is that trustworthy to me means that the system is worthy of your trust, and that should be measurable. So the system should, you know, there should be claims about a system that it is secure or it is fair or whatever else it is. And then it's up to you as an individual, and you should think it's in a certain circumstance, whether you accept that or not. So whether you trust it will change based upon your personal experiences with that service, with other services, etc. What the requirements are, what the risks are. So it's definitely not trusted, but trustworthy is what we want to do. We want to have some way to say, how do we measure these systems? So within our program of work, and this is the program of work that we started 4 years ago, and I won't really talk about what we're going to do next too much, but I'll talk more about what we did. What we wanted to look at was, how do we define trustworthiness? So we chose 6 facets that I will go into a little bit further on. But let me just tell you about some of the identity challenges that we've seen. So you may have been aware that there's a digital identity system in Pakistan called NITHECS, and that was compromised. But in Pakistan, there was a challenge because there were some protests in the major cities against the government. And actually, the government, a government spokesman said that anybody who had been involved in those protests would never work for the government again. And that can raise serious concerns about facial recognition systems. Yeah, because if you have those records with a digital identity system, what you are supposed to be doing is a one-to-one match, right? Somebody presents a credential, and then what happens is you should check that that credential is belonging to the person you think it is. So that would tell me, is that Francesco in front of me or not? But if you have the ability to do one-to-many, I get a credential from somebody, I don't know who it is, and I can check it across the whole database, that becomes a serious risk and violation. And those kind of problems have come up recently in the last couple of years in both India and in China. There was also a problem, and I should point out that the reporting on this is not too accurate in the way that it works, but I'll give you the story of a scenario behind it. But there is definitely an Afghan biometric database, and after some conflict, some devices were left behind that had biometric data access with them. Now, the thing is, the access is not going to be all local, and that's where the story is a little bit incorrect. But if you think about it, if you've got access to a centralized system and you leave in a hurry and somebody can access that, now you've got the possibility to identify people who should not, and people can access the system that shouldn't have access to it, right? Sometimes there'll be caching of that as well. So at the University of Warwick, we do some work on computer forensics, and you'll know that those records can be maintained. So that leaves a serious challenge. There have been claims about Argentina's identity database being hacked and being offered onto dark web. So these serious things, and we know they happen across the world, so it's not new. And when I say across the world, this was really interesting because there was a German art activist. So she was actually an artist, and what she did is she managed to get a German passport. Yeah, but it was not her face. Yeah, so I actually have a UK and a German passport. German passports have had biometric detailing for a long time. Yeah, and that's about measurements so that you can check certain things. And what this lady did is she actually did something called, you may have heard of deep fakes, right? You've heard of deep fakes a lot, but there's something that we call cheek fakes or shallow fakes, yeah, where one can just use some tool like Photoshop and merge two images. So you can do that quite manually. If it's more automated, it's a deep fake. But she used a fairly standard program. She wasn't an advanced programmer or anything. Created a program and created something, a biometric that meant that not only could she use that document, but so too could the it was somebody off the internet actually that she's got a picture of, I think someone famous. So too could that, because it was betwixt the two identities. So these things about compromising systems are very real. And what we have been working on is managing the risk, looking at the risk, and risk is a term that's very important. These days, lots of people looking at risk of AI, but what's the inherent risk in these systems? So we're looking at dynamic risk modeling. So we use a system. So I'm sure many of you have heard of supervised machine learning and unsupervised machine learning. But there are also techniques such as semi-supervised machine learning. We've had a few papers in this area using something called variational autoencoders. And they're quite different. Rather than unsupervised, where you don't have classes of labels of elements. So what you do is you group them into similar elements. That's unsupervised. Supervised is where you have some classes. Yes, you might have some pictures of some people, and it might be males and females, and you'll try and classify them because you have some labeled data first, and then you get unlabeled and say, well, that's more like a male or a female. But semi-supervised only takes good copies of some data, or one class. So we use it in fraud detection. So what we do is we get transaction records. So the identity, when you have your identity, use your identity system, it is a transaction. You take those transactions and instead using variational autoencoders, instead of saying this is fake or not, it gives you a probabilistic. It's how far does it vary from the good data that you've seen. So it doesn't tell you it's bad, but it says how likely it is. And that gives us a slightly more nuanced way rather than saying yes or no, it's good or bad. So we've been working on that dynamic risk modeling, using that MOSIP system. So we have a sandbox at the Turing now, which we're starting to populate with some data using only our experimental data, I should say. And we're doing some work on privacy enhancing technologies, and that's going to be the main technical bit that I talk about to you today. We look at real-time governance. How do you adapt the system and make sure that we do fundamental work? We develop some code bases. So we've released on the Turing's GitHub page, we've released many code bases. We've released more than 70 reports, either academic papers that are peer-reviewed or other working papers over the last 4 years within the Turing. But one of the things that's important is our work to support this trustworthy identity, which is a framework. So the question becomes, I mentioned about how trustworthy is an ID system. So you can develop and design and develop a digital ID system in many different ways, okay? And there are many tools around there to do that. In Europe, there is some kind of convergence around something called EIDAS, which is a format and system for digital identity that allows some interoperability. There's work globally, including, as I said, the MOSIP work, but also Gemalto, now branded. It's been a Thales company for quite some time. Thales, IDEMIA, they all have systems for digital identity. And what we wanted to do is say, okay, how do we check to see whether this system adheres to good practice? So what we did is we did some really significant work analyzing technical reports, standards from a range of areas. So some in cybersecurity, so some ISO standards, some NIST standards, some guidelines and recommendations, and some of the most significant peer-reviewed articles. And what we did is we formulated a set of metrics. So it was a huge set, it's too big really, to satisfy some of these elements. So some of them are in the design. How do you design a system? And some are in operation. So the operational metrics are things that you can gather. So a standard for any kind of IT system, a standard kind of metric would be what's your service uptime? Yeah. But a design metric might be something about how many times do you allow somebody to change their password, or do you use multi-factor authentication, etc. So we pulled out from our work, we pulled out a series of 6 pillars that I'll talk about, a set of mechanisms. So for example, here's one example. If you've got security, you need good access control mechanisms, yeah? And if you've got those access control mechanisms, you've got a set of metrics that you can define. So sometimes they will be very quantitative. So the one I mentioned about system uptime is quite quantitative. Other times they will be a little bit more subjective, a little bit more qualitative. So that kind of work is, for example, if you have ISO 27001, if anyone's heard of that standard, if you've got ISO 27001, it's a security standard, but it doesn't necessarily mean you're really secure because you've met that standard. It will ask you, what are your processes and procedures if you have a breach? Yeah. And it's sort of like a form that you fill in and you get assessed against ISO 27001. But it will say, who is responsible for this? Have you got a named person responsible? And that will be just a yes or a no. And if you get enough yeses at the end, you will receive the ISO accreditation. So we have that mix of things which are like that. Other times it will be something a bit specific, which says, what is the concrete security? So by concrete, I mean, you know, with real techniques available today, yeah, do you use an appropriate mechanism for encryption? So you might have symmetric key encryption like AES 256 bit, and you can give a score against that. Yeah. So and the reason I say concrete is because we're looking at today's challenges. So we're not about what would be great, you know, not necessarily are we looking at quantum resistance right now, right? So NIST has got some guidance and we've been working with them on that. But we designed this framework, and these were the 6 facets that we put in. So we thought, you know, is it secure? Yeah. And built around the CIA triad because it's still tried and tested. It's used a lot. And actually, even if you use the information assurance 5 pillars, you can sort of get them into a CIA kind of framing anyway. We looked at the ethics. How transparent is your system? How explainable is it? How fair? And it was interesting because at ID for Africa last year, we went and saw a lot of presentations, and so many of the presentations said, our system is really fair, you know, our national identity system. I thought, that's fascinating. I said, how did you measure that? And they didn't have answers, right? And then I spoke to the vendors because it's an expo as well. And I said, you've claimed that it's a fair system. What evidence have you got of that? And there was nothing. And it was strange because it reminded me of 4 years ago when everybody in Johannesburg was saying, we do privacy by design. I said, well, what does that mean? What techniques do you use? They hadn't heard of homomorphic encryption or secure multi-party computation. So what they meant is we think privacy is important, and we thought about it when we did this. Not that we did anything, not that we designed it in, but we thought it was important. We look at resilience, robustness, and reliability. So the key thing with reliability, first of all, is it repeatable? They keep doing the same thing. If somebody doesn't get into a system, do they keep not getting into a system so we can work out how to manage that, or etc.? Is it robust? The kind of things with robustness are, if we've got unexpected data or events, does it still work? Can it withstand that kind of perturbation? And is it resilient? And by resilience, what we really mean there is its ability. If you think of security as the protection mechanism, resilience is about how it can recover if there's been some kind of compromise. And actually, my own group, the Academic Centre of Excellence in Cybersecurity Research, we are NCSC recognised. That's the National Cybersecurity Centre. But for a long time, even though it's cybersecurity research, we've talked much more about resilience. And that's because we should all recognise that it's not if you will be attacked, it's when you will be attacked. And it's how do you recover from that? How do you act? So that's resilience. So those are the 6 facets. We have a tool that we're working with governments now where they can measure each of the 6 facets. So you get along 6 facets, you'll get a score out of 5. What's important about this metric is this framework and tool is we do not tell you where you should be. You can't tell a government you should have 5 for privacy, because privacy is in some ways, you know, very cultural. Some cultures are much happier to share information, and others less so. So what we do is we give a score, and it's on a scale of 1 to 5, just to keep it nice and simple. But for each of those 5 facets, you can drill down and say, where did that come from? Yeah. Some of those entries, so you've got to populate this, and that's why there's a tool. But with those entries, some will come direct from system logs. Others will be put in by an auditor. Yeah, it's not an auditor that we say, it's a government. If they want to know their own position, can utilize this. So governments are starting to use this tool to understand where their position is. What it does for us and the community is that it can really help ensure that we understand where the research is missing, or where is something that's too theoretical. And if I give you an example, this is one thing that's happened quite a lot in security. I remember many years ago, a friend of mine, Kenny Patterson at Royal Holloway University in London, one of his students had broken a significant protocol. And what he said is he replied to the RFC. So these protocols, it's an IP protocol, IPsec. So Kenny was quite pleased that he and his student had broken this protocol. So they responded to the author of the RFC and said, we've broken your protocol. And the response he got was very, well, it was rude, basically. He said you hadn't broken it. And the truth was, when I spoke to Kenny about it, I said, you haven't actually broken it, because it was a mathematical proof. But actually 95% of all implementations had been broken through this, this flaw that was found. And that's because sometimes, even though that you design something, actually implementing it is sometimes not possible. And that was always difficult with one-time pads, for example, that gave you provable security. So, yes, so we've looked at a whole bunch of things. We've shared this this framework that you can see here, where we look at cryptography, we look at the user sovereignty, user agency in the identity system. And we're starting to work with governments around the world on it now. We've already worked with ADHAR, because they've had this advanced system for quite some time. We've had the World Bank and ID for Africa working on it, but we're going to be running those assessments in country in this year. And the reason we're doing that is that we're still fundamental academics, but we need to know the feedback about what does it work? You know, what does work? Is this something that is a tool, but you can't actually use it in practicality? If it is, then we have to readjust it and engineer it better. I talked a little bit about fairness before, and I'm going to talk a little bit more about that now, because this is one area of work that we've been working in. So I'm just going to choose two areas to talk to you about. One is a brief overview on some of the work we're doing on fairness, and the other is on data sharing. But if we look at systems, so we have these facial recognition systems, and in fact, in the UK, there was South Wales Police tried to do some trials with facial recognition systems. And a citizen, Ed Bridges, took the South Wales Police to court and said, you can't do that. It's human rights issues. So LFR, live facial recognition, is a big controversial thing, but it's part of digital identity. And actually in the UK, South Wales Police lost in the High Court their case. He had 5 main claims, and some of them were not seen as appropriate. So what he said is, you are storing my facial image when you do a match. And actually, his argument was, well, if ever you have a camera and it takes an image, then even if you don't store it, for a split second, it's in memory, and GDPR says you shouldn't do that. And actually, the court ruled against him on that. It's not really storing it. I know you could argue it is in a sense, but they refused him on that ground. But what they did is they said, he made the argument, and he was a white British guy. He made the argument that it wasn't fair. And actually that was true. Yeah, because there was many tests that showed that it wasn't. And what happens is that if you are of a certain ethnicity, then you're more likely to be pulled up, right? Because there'll be a misrecognition of you. And that's a challenge. So people go, well, it's okay. It doesn't matter, because the police would argue, right? That there were a couple of things. First of all, there was a corridor that you went down. It wasn't a physical corridor, but the sort of corridor where they did the recognition. They said, you can bypass that, and then that's your opt-out. But of course, you can't really do that, because if you opt out, then you get a suspicious look. What have you got to hide? Yeah. So you're actually having this small impact that needs to be managed, and they didn't think about it. But if you went down this and you were misrecognized for somebody, so they had a real data set of people that they wanted to stop. They were wanted for some reason or other. And they argued, well, if you get stopped, what happens is we'll just say, we'll ask you some questions, you'll provide some ID, we say, oh, it's not you that we're looking for, thanks, and you go on your way. And they argued, well, that's okay. So we're not arresting them, they're not having real harm. But this is where we think about what is a harm, because why should I, in that case, it was unfair if you were darker skinned. Why should I, if I had dark skin, be stopped on my way to work, where somebody who had fair skin, or somebody who was male, because it was males and females, it discriminated against? Why should you be stopped, even though it's not going onto your record or anything like that? So actually, that case was upheld for those reasons. And these are there's a Maryland testing facility, there's some work that was presented at ID for Africa that when I was speaking about our work, and you've got a number of different faces here. Might be hard to see it in here or online, but what you've got is the chance of being misrecognized. So you can see it says face 1 through to face 5 and then iris. The face 1 to 5 are some of the major commercial tools out there that will do facial recognition, including Microsoft and others. Yeah. And what you can see is, hopefully you can see, does my mouse come on there? Yeah. you can see it's slightly redder around here and around here and around here. Yeah. And what that is detecting is effectively it's proxy for how likely are you to be misidentified. And you can see here there were 4 categories: black female, black male, white female, white male, and other. Yeah. And in all 4 cases, you can see in the bottom left there's a darker square. And that is because if you are a black female in any of these 5 systems, you are going to be more likely to be misrecognized. So if you have got an identity system, yeah, one can translate that to you might be misrecognized, or you might be denied something because it's not unique enough or distinctive enough. So this is a problem. Actually, on the bottom right, they show iris and show that that doesn't have the kinds of problems. But iris is somewhat intrusive. It can be. We've got better cameras now, but you can't do that all through Africa as easy as you can with a cheap camera. So you've got this problem about diverse demographics. So we've been working on this for a little while. And the idea is we wanted to say, well, why is this working? Because all those 5 algorithms, those major algorithms, all had the same kind of inherent problem. So it got us to start looking at, is the problem the algorithm or is the problem the data it's trained on? And I'll show you some things. So this work's still ongoing, but we'll be releasing some big work soon. But what we wanted to do is say, okay, let's have a look. Can we do something that's larger scale, but maybe do synthetic data sets? Can we create a set of good evaluation metrics and a set of tests? And that's what we're looking at the moment. Yeah. So what we're doing is we're generating a synthetic data set of human faces. Yeah. And some of them is generate a new identity from a specific class. Because the easy way to do it, by the way, is if you've got a large data set, yeah, there are techniques such as SMOTE for rebalancing, where you've got some outliers to rebalance, yeah. The problem is, you know, let's say I had those 4 categories from before. What I could do is if one of the categories is only in 5%, represents 5% of my total sample size, without doing some nice trickery, if I wanted that to be balanced, I've got to throw away 80% of the data set. So I've got this thing, do I work with a smaller data set for training, or do I work with a balanced data set? Yeah, and actually neither's sufficient at the moment. So what we're trying to do is say, can we generate some new identities from a specific class? And I'll talk a bit about that. And can we generate multiple realistic images for a new individual? So typically, a system will have, you'll have a classifier, yeah, and you'll have a reference image. Yeah, remember I said about 1-to-1. So the question will be, is this person that's I can see on this video feed or this fingerprint scan, is this person Carsten that I've got recorded in the data set? So one of the things is if you've got problems because of, as is recognized with different skin types, yeah, and different lighting conditions, can we artificially change the lighting conditions to create a better training system? So instead of having training where everything's just with one luminosity, that we can change that. So what we want to do is look at some latent space exploration. So look at the latent space, so further into the deep learning networks, so not going all the way, but just peeling away a few layers. So we've worked on this, creating a set of generators. So we learn a common base structure across all our classes, in this case 4 classes, and we scale it using our GAN. So these are some of the synthetic faces that we've generated, and you can see here some synthetic faces are very good and some are not so good in our set. And this is true of all synthetic data sets that you get. like this. Some of them, there's there's one particular company that's released a lot of data, and I think it's Microsoft that's got a big synthetic data set. I'd encourage you to look at it because some of them just look completely like computer-generated avatars, not like. You can see some problems we have here because we've shown some things with the mouth in particular where it struggles. But you can have, when you've got unbalanced data sets, you can get something called mode collapse. It doesn't give you diversity in your population. They converge to look similar issues. So we've got a number of strategies that we've been using to avoid mode collapse. I won't go into them too much because I want to spend a bit more time on something else. And we've got some new improvements in our synthetic data that we've got. So here are some synthetic images that we've created. One thing I wanted to do about this is when we first started doing this work, those classifications, black male, black female, white female, other, I recognized a bit of a challenge with that. When we were looking at it, I said, but we've got a lot of discussion about gender fluidity now. We've got a lot of things. I don't know if it did. Does anyone remember seeing that thing about the gaydar detector? So it was a machine learning algorithm that said it could work out if you were gay or not. Yeah. Very controversial because, of course, how do you where's the ground truth in that? And the same happened for us when we were doing things, and said, so my researchers were doing, oh, look, it said that this is a black female and look, it's clearly male. And I said, how are you, this is for my research, I said, how are you qualified to say if that is a synthetic image? It's not a person. So how can you say, well, you can say it looks male to your eyes and your context, but that led us to move away from that and talk about these kind of classifications. So there are certain characteristics. So this isn't male as in your gender. These are very much about characteristics, and they're not about ethnicity, but rather about colors that we did. So we split this into 8. And what we see in a real data set, this is the kind of thing. So we've classified instead of males, females. Well, we've used these females and males are these sort of characteristics instead rather than true labels. And we've got the skin types. Now you can see here this difference that aligns to those black females that we saw before. So dark females, 72% chance of being correctly identified. Whereas if you were male and light, it is 87.6. So what we've tried to do is look at, okay, what about this balancing idea? So we've done some balancing. I told you before where what you do is you take the lowest number that we had, which is 92,000, and we retrained a machine learning algorithm. And this was the baseline before. And then just doing something balancing that, there's no great trickery here. One can see that they're not very good in either case, but the most interesting is they're a bit more bunched together. But the key thing is it's now not discriminating against, for example, white males, which are typically the best that are classified, was now not in this balanced data set. So there's some work there that tells us if we can balance, we might not get good accuracy, but we might not see those issues that we've seen previously. So this is what we've done with synthetic data sets. So what we're showing now is those elements across dark and light and red and yellow. The real data sets that have been used are pretty heavily balanced, into light so they're low hue and high luminosity. I can't remember which way that works on white or red. But what we've done is we've used some generation techniques using conditional generative adversarial networks and got a much better balanced data set. So these are 24.46 in the top left corner, 25.92 in the right. etc. And that is giving us, so what we've got now is a technique, and I'll be able to share some results soon. I was hoping to share them today, but they're just coming, so they're going to be hot off the press soon, not today. But what we've got is a technique now to generate synthetic faces that is much more balanced, so it doesn't have that problem of only limiting you to the lowest size of class. And we know that if you've got a more balanced set, you're going to remove some of those biases. So that's one large piece of our work looking at fairness. We've got lots of other work on fairness as well that I can't go into today. But I did want to go on to something on information sharing because, as Francesca said, and I know some of you work in finance, there's some work that we've been doing on a large project, about £13 million project at the Alan Turing Institute. It involves the University of Cambridge, Oxford, Warwick. I lead on security and privacy with a colleague from Warwick, Edinburgh, and no, I think that's it. So those 4 institutions. But this is a framework for responsible AI in finance. So there's a number of elements, but I'm just going to talk about one in particular. Yeah. And that is around data sharing. So when we've got these systems, we sometimes need to share information across different parties. So sometimes you will need to know, let's say there's been some migration, forced migration or not, and you want to check, has somebody had some kind of aid or some kind of problem in one country and then in another. So they might be in 2 disparate systems. And the question is, how can we check and do what's called entity resolution? So this is an old problem, entity resolution. But what we need to do is share data that complies with law and regulation and governance. And that's one of the main issues at the moment, that actually GDPR in Europe is a data protection. You can't share information. But what we're seeing increasingly on this work is not only in an identity space, but also in a finance space. There's strong regulation in China that data about individuals in China cannot leave China. So the question becomes about, how do I check if I've got 2 data sets, whether the same person is in both data sets? So if you can't do that just by shipping the information, what techniques can you use? Well, and we've been doing this work on privacy enhancing technologies. So this work is that there is at the Royal Society in the UK, there is a working group on privacy enhancing technologies. Both John and myself are 2 of the 10 members of those teams. And we've worked on how do we use privacy enhancing technologies to get some shared intelligence, yeah? And that can happen even, I gave the example of one example is a bank that's got 2 branches in different jurisdictions. They can't share information, but actually some government systems cannot share information. In fact, one of these major issues when I was at MIT a few years ago, there was a talk at CSAIL about this, and they were talking about no-fly lists and the fact that the FBI, Department for Homeland Security, and CIA cannot share data lists, right? They can't share them because you don't want to be on one list for some erroneous problem and then end up on 3 lists, right? Because then you are really in trouble. But what they'd want to know is, how can we see if there's somebody that's on all of the lists or so many of the lists and on a no-fly list? Yeah, so these privacy enhancing technologies can help. And there are lots of privacy enhancing technologies that we can use. And we've done work at the Turing and at Warwick on probably half of these at least. And the interesting thing is, for those that you know about something called federated learning, anyone heard of federated learning? So federated learning is something that Google came up with. And interestingly, what they said is, we've got lots of analytics. We want to learn about people, but there were concerns about these central data stores having everything, them knowing everything. So they said, got a great idea. What we'll do is all the data stays on your phone, yeah, or your device, whatever it is. And what we'll do is we'll create a global model. We'll send the model to your device. You tell us how well it fits. Then what we'll do is however it fits, good or bad, we'll feed that back to the central model. We'll change the global model and we'll keep moving it up and down, and we'll refine so that you learn from the global characteristics, but you have a local model as well. And the problem with that is, so everyone went, that's brilliant. Data never leaves the device. The problem is, though, if I take enough measurements of your data, then after enough measurements, I can just recreate your data. So then they had to start combining things, and they brought in then, okay, let's have secure multi-party computation. And they said, okay, oh, but we need differential privacy, which adds noise to the data as well. So actually, we often have to use these in combination. So I'm not going to go through these because I've only got 5 or 6 minutes to go. But actually, today, in fact, I should say, one of those, today we just got the announcement from KDD. If anyone's heard of KDD, it's a pretty good conference, takes place every year. Our technique is federated learning using differential privacy and synthetic data. So it's a mechanism called FLAME. So it generates synthetic data from distributed devices using federated learning, but each has some differential privacy. So that paper's on archive, but will be published when the conference is out, acceptance, as I said this morning. So what we have to do is we have to combine a whole host of techniques. So let me just show you. Right. Okay. So what I'm going to show you is one of the more difficult problems we're starting with, which is around fuzzy name matching. So, for example, one of my researchers working on this is from Turkey. His name's Ilke Atmarka. And for me, that's quite difficult, A, to pronounce, but B, it's quite difficult because I don't know which is the first name and the surname very easily, right? And the reason is he has 2 first names. Yeah, I have a first name and a second name, but they're sort of equally weighted. This happens in other countries where people might be called Raj, for example. It might be something. In the UK, people might have a family name, yeah? But we typically say that's the first name. But in Turkey, what will happen with he's got a position at Warwick and at the Turing, and they are different the way that they've classified the name, because in one of them, it's Ilke, one word. In another, it's Ilke Atmarka, they've joined the Ilke. This creates some kind of challenges. How do we do this name matching if it's not exact recorded? So when it's exact, there are some very nice techniques that you can use from secure multi-party computation and homomorphic encryption. But we want to be able to solve this problem. Yeah. So how do we do that? Well, what we do is something called locality sensitive hashing. So one of the best examples to think what locality sensitive hashing is, well, first of all, I'll tell you what a hash is, right? I take an element, and a hash of that is a unique representation of that single element, such that if I change this in any small way, even the smallest way, it creates a hard to determine change in the hash value. Yeah. But what it can be used for then is if there's any little change in this, I can tell because the hashes now don't match. And that's really good if I've got a document where you've signed it and then I change it and put an extra 0 in or something like that, right? Locality sensitive hashing, on the other hand, is quite different. I should say with this, you can have a problem of collisions because the space for the hash is much smaller than the original space. But locality sensitive says, okay, let me make some changes to this, but it result in the same hash, yeah? And this is how we do things like reverse image lookup, yeah? Because it takes some information from from the element, but it says, well, I'm going to store it as a hash, and it shouldn't really be called a hash, but a hash where if I rotate it, it's exactly the same. And that's what allows us to look up those, but that's called locality sensitive hashing. So what we do is we take a word. So think where it says that general hashing, you see that? Think about these little segments as being parts of words. So they could be trigrams, for example, that's what we do. And we say, okay, well, let's take some generic measurements of this in such a way that two different, but essentially related in some sense, elements have the same hash value. Yeah. So that's, as I say, if you take a photo and you crop it, reverse it, it creates a hash, and that's how reverse image search or TinEye, those kind of things work. So what we do is we do locality sensitive hashing, so that it allows us to consider how two elements that are not the same can be matched. And you've got a problem there, because there could be problems because you can have mismatch. So you've always got that issue. So what we do is we have a querier and a responder. Yeah, and the querier, what they want to do is check, is my name, this name I've got, is a perturbation of it in your data set. So what happens is we send some elements, yeah? So A is the querier, yeah? So what it does, it sends a locality sensitive hash of a name N, and it sends it to B. So this can be really quite challenging, right? Because now I have to try not to reveal much information to B, because that's our privacy thing. So what we do is we set all of the elements in B into a root D by root D. So imagine there's D clustering. We send the encrypted, yeah, so this is homomorphic encryption now. So homomorphic encryption means I can send something to you that's encrypted. You can operate on it, but you don't see what it was. Yeah, so I've now got the querier sends me as a responder a name. It's in the encrypted domain, and what I can do is I can put all of my elements into the encrypted domain, yeah, and then send back for each of those root D rows, I send back which was the closest row, yeah? But I don't know what it is because I've done all this in the encrypted domain. So in the encrypted domain, I send back to A and said, look, okay, I've got some centroids for each of these root D classes. I'm going to send you the cosine similarity scores, yeah, that's encrypted, that only A, who has the key, B never receives the key, can now decrypt that, compare them, and say, right, I know which of those root D rows is the closest to the name that I've sent, yeah? So then what they do is they put in the encrypted domain a set of zeros and ones, and they send that back to B. Now, B's just got this encrypted thing, right? It doesn't know which are zeros and which are ones. But what it now does is it says, okay, I'm going to take those zeros and ones, and I'm going to multiply each of my columns by that 0 and 1, yeah? And what that does is everything that was not the closest row goes to 0, right? It's close to 0, not exactly 0, because it's in the encrypted domain. So homomorphic encryption introduces some errors. It sends that over to B, and now B can work out, do the multiplications on each of the elements row-wise, sums each column, and returns the root D score. So what this tells me now is the first time that I sent across the cosine similarities, A has learned which of the rows I was in, yeah, which row the closest element in. Now, this time, because I've done a matrix multiplication, it will now tell me which of the columns it was in. So now, at this stage, A can find out what the received vector is. It can find out which cluster and which row it was, and how close it was. So it doesn't learn anything else within B other than how far is the closest element. So we've done some testing on this with a number of different clusters. We've had to do things that reduce the communication overhead. When you do some calculations in the encrypted domain, homomorphic encryption, a few things happen. One is you have to pad out, so it makes your element a lot larger. So there's a storage problem and a communication problem. And there are errors that are introduced because you're working typically on lattices rather than in discrete fields. And we've run some tests on this. So this work actually is going to be subject. HSBC are applying for a patent on this work in China and are going to be using it to match data. What we've done is we've done some sensitivity analysis using the Levenshtein distance. The Levenshtein distance is how far apart two different strings are. And we've run on the US Census data set, so that's a publicly available data set that can use, and we've used a data set of our own. I won't be able to go through that. I've somewhat rushed some of that at the end, but those papers, I've got papers for all of these. I just wanted to give you an idea of what we're doing in two areas, homomorphic encryption and fairness in facial recognition systems. And I'm more than happy to take some questions now or some other time. Thank you.
Yeah, thank you very much for the excellent overview. Maybe we can switch on the light now. If it goes on. Yeah. Thank you very much. Are there questions for Carsten?
I was wondering,
Can I give you the microphone so that the people online can follow?
I was wondering on your slide with PETs, you mentioned zero knowledge proofs. So any publications there or work that I can look at related to zero knowledge proofs?
Yes, let me see. I will send you some on zero. We're doing some work right now on zero knowledge proofs for identity systems. We're doing some work, it's around zero knowledge proofs in multi-party computation. So there's a piece of work by Lichun Chen from Surrey called MPC in the Head. So we're taking some zero knowledge proofs in that, and we're just expanding to try and get something that's sort of tractable but provably secure, in a sense that what you're doing is, rather than giving keys, you're just proving. In this case, you know, with a zero knowledge proof, you can have non-interactive or interactive. So what we're trying to do is get something that's non-interactive for NPC.
And I don't want to hog the microphone, but one more question, then I'll stop. So in terms of fairness, so you've done work around image recognition, but when it comes to just textual data and word embeddings, there's also interesting examples there of fairness where the typical example where you take programmer minus man plus woman, you get housewife and things like that. So there's all kinds of interest there. So have you done anything around fairness, but it's textual data and perhaps around word embeddings and so on?
Yeah, so there's around that, what we're doing is we're doing some testing strategies. So I mentioned before about the AI Safety Institute in the UK, and it's called AI Safety, but it's largely around LLMs. That was the thing that powered everyone to look at that. And what they're doing is creating some fairness tests. They've just released a framework. Their fairness is a small part of it. We're doing a little bit more in a sense, but we're concentrating on outcomes from LLMs. How fair is that? So some of the similar kind of things, but that project only started 1st of May. So we're just looking at that.
Thank you.
Any other questions? Donovan, please.
Hello. Okay. So it's a question regarding the facial recognition or pretty much any biometrics in general. What is the similarity measure that they typically use for this stuff? And what is the threshold? So when is it a match?
Yeah, so that depends upon your system,
Okay.
right? So typically it will depend how you've trained the system, first of all, what data it's had. The thresholding is, so what happens in the systems that we work with, there'll be a sort of ABIS integrator. So they will have their own techniques and they'll fine tune based upon, because your whole point is you're trying to balance false reject and false accept, yeah? So that fine tuning typically will happen by some samples that people have done. So they'll run some pilots first and then try and adjust that parameter. But what they don't look at typically is across different types. And that would be one way you could test the fairness, right? To say, well, we're going to run it across different classes of people. And maybe another thing that they don't look at is what's the conditions. And that's why what we're doing is artificially changing conditions. So you'll know the software that you can change the luminosity of an image. So we're trying to do that automated, because you can't just do it each time manually with one, to try and get that greater fairness. But the answer to your question is that it's piloting that they try and fine tune that parameter.
Thank you.
Can I ask a question?
You're
One
the boss.
area where privacy and identity are closely related is the medical field.
Yeah.
You sort of avoided to mention that, or you didn't mention it. Are you also working in that area?
Yeah, so we have a large European Union project that started in November at Warwick. It's with a number of partners because it's a European project. It works with one of our technical partners is a company called Syntho. And what this is doing is we are looking at how can we use synthetic data. The project's called InSafeDare. How can we use synthetic data instead of real data to test the safety of medical algorithms and devices? So we are doing that. But instead of using privacy enhancing techniques that you saw there, what we're doing is we're synthesizing data. So we've got some records, instead of course, you know, the standard thing in medical field is anonymization or pseudonymization. But what we're actually doing is training using synthetic data. So that work, in fact, I think there's a paper that might be coming out soon on that, but the project's only started in November.
If there are no other urgent questions, then thank you very much,
Thank you.
Carsten, for the very nice talk.